Hi everyone, today we're going to be graphing polynomial functions. So as you can see right here, we have a couple steps that are going to help us guide us along when we graph our functions. And when we look at the functions that we're graphing today, everything's going to be in a factored form, and these are intended to be sketches. It's something that you can do without a graphing calculator. Once we get into applications, we'll look at some of the more specifics, and we'll use a graphing calculator for section 3.5. But until then, we don't need to worry about that. For the most part, when we've graphed linear functions in grade 10 and quadratic functions in grade 11, we've been very precise. We've graphed exact points, and we've made sure that we label our points, and there's a minimum number of points that you have to have on there. For this part here, we're looking more at characteristics and trying to get a sense of what could functions look like when they're greater than degree 2. So example 1 here, it's asking us to graph y equals x minus 3, x plus 2, and let's just see what we know about this already. So we take a look here, and we could say, well, we know that we have zeros at 0, 3, and negative 2. Okay, that's coming from here, here, and if you just have an x factored out in front, that produces a 0, 0. To find the y-intercept, we put in 0 for x, so we substitute in x equals 0, and we put in a 0 for each of these x values right here, you would be left with 0, 0. And the degree is going to be a third degree, and that's because if you were to FOIL and expand that, you would have an x times an x times an x, so there's 3 x's there, making it third degree, and there's no negative that's been factored out in front, so we're going to say this is a positive third degree function, or better known as a cubic function. Our zeros are at 0, 3, and negative 2. So along here, the x and y axis, you can just estimate where 0 would be, 3, and negative 2. So here we go. And then based off of that, we're just going to join these into a positive cubic function, just like what we had learned from last class. And so if we take a look at this, we could say, okay, a positive cubic function has the behavior of something that would look like that, where the terminate, or you extend out into quadrant 1 and quadrant 3. Now, we're not being exact here in terms of what our minimum and maximum points are, and we haven't labeled any of the heights or the values of the y-axis, but that's all that they're asking for in this particular question. Okay, so let's see what happens when the examples get a little bit more complicated. Okay, example 2, here we have something in which there's two things that are new to this question. The first thing is this says x squared, and the second thing is this says 1 minus x. And so just like we've said so many times before, we want to put this in what we would call ready form. And so that means we should factor out a negative 1 from that 1 minus x to make it a little bit more proper. So let's do that. And what we could say is if we factor out a negative 1 and we put that in front of our whole function, then we would have something that would look like this. That would produce zeros of negative 1, or from last class we learned that could be negative 1 with a multiplicity of 2, positive 1, and positive 2. The y-intercept, well, what would happen if you put in 0 for each of the x's? You would get 1 times negative 1 would be negative 1, times negative 2 would be positive 2, and then times a negative sign would be negative 2. Okay, and the degree, well, if you were to expand that, that's a fourth degree, and because we had something where we've had to factor out a negative, this is going to be a negative quartic function. It's going to open down. Okay, so what would happen now if we started to estimate where this would end up? We have something happening at negative 1, 1, and 2. And we're going to draw a negative quartic function, meaning it's going to look like the letter M. But the other thing that's new, the second thing that we said was going to be new, is this -1 occurs twice. And we'll go into a little more detail for this, but when you have something that has a multiplicity of 2, we're going to say that's going to produce what we call a bounce. Okay, so it's going to not go through the x-axis, but it's actually going to reflect back down and stay below the x-axis. So as we start to join here and we go to -1, we can't go, it hits and then it comes back, and then it goes back up here and then down here. Okay, make sure you put arrows down at the end. So a common question you're probably thinking right now is, well, why do we have this bounce right here? So what I would recommend is think about an example of something that you are familiar with. If we were to do a sketch of something like y equals x minus 3 squared, that would be a parabola. It would be a quadratic that would open up and would have an x-intercept happening twice at 3. And so if you were to graph that, it would look like this. It also means then what happens is if you would put in a number bigger than 3, because it's being squared, it's going to produce a positive output. But if you pick a number less than 3 and you produce something that's negative inside the brackets, when you square it, it produces a positive. So there's no sign change. If you were to do something called a sign diagram, it retains its same positive features. It stays above there, and that's because we have a double zero happening right there. And so that same characteristic is what's happening here, where we have this bounce right here at -1. Okay, so example B. Now we have something in which we have a multiplicity of 3. So our zeros here, there's nothing to factor out. Our zeros here would be 3, -2, -2, 1, 1, 1. And if you're to expand that, that would be something that would be a 6-degree polynomial, and it's going to be positive. There's no negative that we had in front. The y-intercept, if you put in zeros there, you would get -3 times 4, which would be -12. -12 times -1 would be +12. Okay, so let's see what our sketch would look like here. We have something occurring at -2, at 1, and at 3. We have a positive 6-degree function, and it's going to go through, it's going to start high, and it's going to hit the -2 twice. So we have our bounce happening right here. Okay. Then it's going to go up, have a y-intercept of 12, come back down through the 1. But when it comes down through the 1, we now have something that has a multiplicity of 3. We could expand on this a little bit more, but right now let's take, let's say that whenever it has a triple 0, it's going to be something that hangs out there. So if a double 0 was called a bounce, we're going to call this a slide. Okay, it's going to hang out there and go down below, and then it comes up here through 3 and goes up. And if you want a little bit more of an explanation as to why it slides when you have a triple 0, imagine, I know some of us has graphed y equals x cubed. Think about what that looks like when you graph that. It goes through 0, 0, but it hangs out there, and then it accelerates really quickly after that. And so that's that same behavior that's happening for this example down here when you have a triple 0. Okay, a polynomial has -1, -1, 0, and 2 as roots, and it has the point. This is a fancy way of saying it has the point 1, 5. What's the equation of the polynomial function? So we know that we have y equals, well, what do we know? We have, it has an x plus 1 squared, and it has an x minus 2. And in front of here, we don't know what its expansion, like its vertical expansion or vertical compression value would be. But we're able to find that out because we know an additional point. We know the point 1,5 passes through it. So we're going to put an a here, and that's our unknown. That's something that we need to be able to figure out. So based off of that, what we could now do is we could say, well, I know an x value and a y value for a point, so I can sub that in for x and y, and then based off of that, I can solve for a. So we would get 1 times 2 squared, so 4 times -1, so we get -4 times a. And then based off of that, divide by -4, divide by -4, and our a value is -5/4. So we should write out our final solution, and we could say something like y equals -5/4 x plus 1 squared and x minus 2. Okay, so given that, I would pause the video right now and I'd say answer 3B on your own. Okay, pretty similar question to the one above. We could say y equals, we don't know the a value, but we know that it has an x minus 5, x minus 2, and x plus 3. We also know that it passes through the point 1,8, so we could sub that in for x and y, and we can find out our a value. So you could say 8 equals a, and then every time there's an x, we'll replace it with a 1. And so here we get -4, +4, +4 times 4. We would get 16a. And our a value is going to equal 1/2. So then, once again, let's rewrite what we have for our entire function, and we'd say y equals 1/2 x minus 5, x minus 2, x plus 3. Okay, example 4. So pretty similar also to example 3, but now we can see things a little bit more visually. And what we need to be able to interpret for this is it has an x-intercept at -4, and it has a double zero happening at +3, because clearly this is an example of having that bounce. So the 3 is occurring twice, and this is representing a negative cubic function. So we know that our a value is going to be negative because of the direction that it's pointing to. So we can say y equals, we don't know the a value yet, but we know that we have something where this would say, well, the 3 is occurring twice, so let's go x minus 3 squared, and then x plus 4. And it goes through the point 0, -18. Now, I know no one would do this on an assessment, but a really common error is that people sometimes think that, oh, that means I could just write -18 at the end there. And we don't want to do that at all. In fact, that would only be true if you put in 0 for x, would you be left with that -18 there, and that wouldn't be the case. So we want to sub in the point x, y, 0, -18. -18 equals a. 0 minus 3 squared, 0 plus 4. And here we get 9 times 4, 36. So we get 36 times a. And our a value will equal negative 1/2. So then we could say y equals negative 1/2 x minus 3 squared x plus 4. Okay. Example 5 is a little more theoretical. So they give us some characteristics. They're saying a is less than b, which is less than 0, meaning that a and b are both negative values, and then 0 is less than c, meaning that c is going to be a positive value. So let's see what we could come up with something like this. So the smallest x-intercept that we have is going to be located at a, and so we could say, okay, well, this is just a sketch. A could be somewhere around here, B could be somewhere around here, and C could be somewhere around there. But we know that C has to be a positive value and A and B are negative values. And we also know that B has a bounce because it's occurring twice right there. And so if we're to get ready to graph this, we know that we would graph, we're going to graph something here that, well, there's no negative in front, so let's assume that it's a positive quartic function, and it could look like this. It's going to bounce off of b twice, and that would be something that would satisfy all of those characteristics. And right here we have our y-intercept, and our y-intercept, well, if we put in a 0 wherever we have an x, if we put in a 0 here and here and here, well, what would end up happening? We would have something that would say negative a, negative b squared, negative c. And if you're to times those all by each other, it's going to equal a b squared c. And that's our y-intercept. And so even though it looks like that might be a positive value, as you can see, it's located below the x-axis. So it's a b squared c is representing a negative number. So then it says, well, what's the solution when your function is greater than 0? Okay, so if your function is greater than 0, that's a fancy way of saying when is it above the x-axis. And so it's above the x-axis right here and right here. And so two different places. So we could say that's everything to the left of a. So that's when x is less than a, and it's also when x is greater than c. And then the final question says, when is your function less than 0? And so when is it below the x-axis? And it's below the x-axis. Well, it's below the x-axis from, you can say this a couple ways, but I think the easiest way to say it would be it's everything between the a and the c value. It's always below the x-axis between a and c, except when it hits b. Then it's not technically below the x-axis, it's on the x-axis. So we would say something along the lines of it's everything between a and c, but it can't equal b. And I think that's the easiest way of saying it. There's a lot of intricate points of different ways you could think about it. If you had a question that said something like, well, what if it said f of x is less than or equal to 0? Then it would be everything between a and c, and you wouldn't have to worry about that b value. But because the b value hits the x-axis right there, it's a little bit tougher to write. You also could have written this as two separate parts. You could have said it's everything between a and b. So you could have said a is less than x is less than b. And then you could have also said where b is less than x is less than c. And that would also technically be a correct solution. Okay, that wraps up section 3.2. Here's your homework, and hopefully that lesson went quite well. Okay, thanks. Bye.